I have 2 slides. I'll come back to them where I do the formal presentation of it. I prefer to talk about it in this example, and then let's go back to the general slides afterwards. This is an example constructed to lead you to the hypergeometric distribution. Let's consider, this is a classical quality control example where statistics and probability, of course, plays a major role out there. What if, and now I'm also speculating, just for the sake of the point, I'm speculating that I know the system. Of course, in real quality control, you don't know what's there, because otherwise you don't need to control it. But let's just, again, think about this funny thing that I know that I have 10 hard disks, and for the sake of the scenario, that's why I'm saying you for the sake of the scenario, let's assume that 2 of them are coming with faults. So we're having 10 products shipped to us from one of our providers, and we are thinking about quality control, and let's just scenario-based think about a situation where 2 out of 10 would be with errors, hard disk with small scratches. What would you do to do quality control? You would take a sample of the 10. If you had the time and the effort, you might check all of it, but usually we don't have out there, so you would think about only taking a sample of what they sent you and then just check randomly, right? Every now and then we go check. For instance, 3 hard disks. Let's assume that I decide to do a quality control by looking at 3 of them. Then I ask the question now, what is the probability that at least one of them has scratches? Now, if I did not start talking about the hypergeometric distribution, you might use and think about the only hammer in your box that I gave you so far, which would be the binomial distribution. Let me try to be a bit naively overdoing it and showing you, if you do what I'm sketching now, the binomial could be the right probability model to use. If I took a sample out of the 10-1, look at it, check whether it's okay or not, put it back in the box, and make sure I don't recognize it again. Putting it back among the 10, shuffling the 10, and running out of the room, let my colleague shuffle, and then I come in the room again, and I take a box again among the 10. I might take the same one again because it's in there. That would be sampling with replacement. And if I do that, if you want to do that, it's fine. If you have the time and the effort and want to spend the money, then fine, do it. That would then we could solve the problem by saying each time I sample 1 hard disk, there would be a 20% chance that I pick one of the 2 erroneous ones, right? Because it's the same thing that happens to us 3 times in a row. But that's not the way such things are done in practice, right? You don't stupidly go and put down a hard disk you already checked. You don't put it back in the pile and with the risk of wasting your time in checking it once again. That's not what you do. You pick out 3 at random, and then you check it, you set it aside, right? So you do actually sampling without replacement. That's what you would typically do in such a case, right? Because it's also, if you think about it, when you're a sample and people call you and ask you what you're voting, I mean, if I manage not to say something grumpy at the first time, which usually I don't, but if I managed, I would definitely be pretty grumpy if the same guy called me again. Hey, you were put back in the pool because we're sampling with replacement. I'd like to know again, who would you like to vote for? I don't think we would be nicely open to it. We don't do sampling with replacement. Most often we do sampling without replacement. And then we have another probability model to give us the right probabilities. It's no longer the binomial because it's not the same experiment. If you take one and set it to the side, I only have 9 left, and maybe I took a fault one, maybe I took the other one, I don't know, but in any way I changed the p. So it's not repeated identical Bernoulli experiments anymore. It's a different thing going on. What is going on? Well, we call it the hypergeometric distribution. Let me try to, without all this here, how should I find, let me see how much I have actually. What is the probability that at least one of them has scratches? At least one means this, meaning that I have to go like this. That's the hypergeometric probability. Let me try to, I don't think I have anything more, but I'd rather like to say this probability of seeing, for instance, 0 with scratches. How do I get this probability? Well, I am taking samples of 3 out of 10. So you can express the hypergeometric by this binomial coefficient if you know what it means. Because I take samples of 3 out of 10. 10 is the total number of the total number of hard disks. That is the total number of possible different samples of 3 you can make. How many of those comes with exactly 0 fault ones? Well, I should take the 0 out of the 2, and I should take the 3 out of the 8, right? The 3 should be among the 8 with no faults, and the 0 should come from the 2 with faults. That's the general combinatorial where you count the number of relevant ones, and then you count the total number in the denominator. If you could follow me just a little bit there, then I go back. I actually just gave you this formula, but explicitly by the numbers of the example, that the hypergeometric is this probability distribution that makes the right counts for us like that. That's a short way of saying it. And it is the one that would be the more relevant, the correct one to use, actually, if we want to be strict about it, when we do sampling without replacement. The final slide on this was where I was. These two are sort of sometimes, in a way, competitors. One thing is that one might, by mistake, think that you can use the binomial, as I sort of sketched the idea, even though you should use the hypergeometric. That's a mistake you can make. However, if I sample people, that is, if I sample 1,000 out of 5-6 million in Denmark, right? If I sample I have a very large n, right? And whether I remove one person or not out of my population of 5 million, 5-6 million, yes, mathematically it changes the system, but not on the first 15 decimal points in any way. So whether you do hypergeometric or binomial, if you have a large n, makes really no difference at all. So for a large n, this is the loose way of saying it, it's almost the same. So even though you do binomial thinking and probabilities, which might be wrong, you will get the right result up to decimal point, I don't know what, anyway, in many cases. It's just to... So these two are sort of competitors. Of course, I may test you that you know the difference on some small examples where I'd like you to know that you should use the hypergeometric, and the only way you get the real correct result would be to use the hypergeometric. So I'm not saying it never makes a difference. I'm just telling you, sometimes in practice, it does make a big difference. The thing is, binomial calculations sometimes are much easier for us than this hypergeometric. So that's why people often use that instead. That was the hypergeometric. One more